right, so this first slide says to rationalize the denominator, okay? And so, you know, we haven't talked about this in this class, rationalizing the denominator, but this is something that you probably learned in algebra, okay? But we're going to review it. So this is like a review warm-up question. And basically what that means to rationalize the denominator is you don't want an irrational number in the denominator. So you only want rational numbers in the denominator. And currently, 1 over the square root of 2, the square root of 2 is irrational. So we want to get rid of the square root of 2 out of the denominator. And in order to do that, we are going to multiply both the numerator and the denominator by the same thing. We're going to multiply them both by the square root of 2. That's going to help us get rid of the square root of 2. So I'm just going to multiply by the square root of 2 over the square root of 2, which is essentially multiplying by 1, right? Because anytime you have a number over itself, this is just equal to 1. This is actually equal to 1. And you can multiply by 1. That doesn't change the value of something, but it does change the way it looks sometimes. All right, so when you multiply two fractions, we're going to multiply the numerators straight across. 1 times the square root of 2 is just going to be the square root of 2, because 1 times anything is just that thing you multiply it by. Then we're going to multiply our denominators. Square root of 2 times the square root of 2. You can rewrite that as the square root of 2 times 2. And then whenever you're trying to get rid of a square root, what you're doing is you're looking for, since this is the square root, there's that invisible index of 2. We want 2 copies of the same factor. And so I have 2 2's that I can pull out, which means that this simplifies to the square root of 2 divided by just 2. Because 2 times 2 is 4. Square root of 4 is 2. You can give it that way as well. And so this is rationalizing the denominator. This is our answer here. There you go. So I didn't cut it off that time. And that's something we're going to be doing today in what we're working with, is we will be working with square roots. And so we do want to know how to rationalize the denominator, so that way if you're asked to simplify your answer, you don't want to leave an irrational number there. Can I simplify it even more? So right now, this is exactly equal to the square root of 2 over 2. Now, if I want to approximate it, then I would take the square root of 2 and divide it by 2. But with irrational numbers, the square root of 2 is an irrational number. Anytime you are trying to use a calculator to figure that out, then your answer is no longer exact. So it would depend on what it's asking you to do in the directions. This is just rationalizing the denominator. If it wanted you to round your answer to the nearest tenth or something like that, then you could go ahead and get some decimal answer for this. But otherwise, this is how we want to leave our answer. Good question. Alrighty. So this out. Here we go. So I kind of tried to update our pear decks a little bit to make them a little more user-friendly. I'm starting to write which unit we're in at the top above the lesson, which seems like a very obvious thing to do. I just never thought to do it until when I was making these yesterday. So we're still in Unit 4. That's why it says Unit 4. We are in Lesson 13.3. And this is on isosceles right triangles. I took out the EQ and just put the learning goal. Okay, so the learning goal is what you want to be able to do at the end of the lesson. I can use special right triangle relationships to solve for missing side lengths. Also, you can see right here we have 10 slides. And so we won't go through all of the slides today. we are going to get up to slide 7, and then you're going to stop. And then we'll come back and do the other slides. We'll do 8, 9, and 10 tomorrow. All right, so that's kind of new. Like I said, I'm not trying to give you guys 2 extra days of work. We're just rearranging our schedule. So we meet every day, not even for a whole 45 minutes, because I'll probably end the meet early on most days. So Monday and Tuesday are for the same Pear Deck lesson. Thursday and Friday are for the same Pear Deck lesson. We just continue it on the second day. Here is your one vocabulary term. An isosceles right triangle is a right triangle that consists of 2 equal length legs. And since the 2 legs of the right triangle are equal in length, that means the corresponding angles would also be congruent. Thus, in an isosceles right triangle, 2 legs and the 2 acute angles are congruent. You can see that in the picture. So the 90-degree angle is where your 2 legs come from, and they both have the same value of x. X is just a variable. Whatever it is, it's the same. And the 2 acute angles are both 45 degrees. They are congruent. And then there's a relationship between the hypotenuse and the leg length. And so that relationship is whatever the leg length is, if you multiply that amount by the square root of 2, that will equal the length of the hypotenuse. So this is just a special type of relationship when you have an isosceles right triangle. Okay, so this first example, I'm just going to kind of explain it to you. It says, find the unknown side length in triangle ABC. So over here is triangle ABC. And we can see that it has a right angle. We can see that the 2 acute angles are both 45 degrees. So this is an isosceles right triangle. And when you have an isosceles right triangle, there's a relationship between the hypotenuse and the leg length. And that relationship is that the hypotenuse is the square root of 2 times as long as each leg. They're telling us the hypotenuse length. So since we know the hypotenuse, we can figure out the leg length, which is the same for AC and CB, or AC and BC. And they kind of wrote out this equation with, I guess you'd say 3 sides to it. I don't know. AB, okay, AB is the hypotenuse, is equal to AC, which is one of the legs, times the square root of 2, which is also equal to BC times the square root of 2, where BC is the length of the other leg, okay? AC and BC are equal to each other. That's something we know about isosceles right triangles. The leg lengths are congruent. If we just substitute out the hypotenuse of measurement of 10 for AB, then we get 10 equals AC times the square root of 2 equals BC times the square root of 2. So these are all equal to each other. And then we can solve it. We're going to multiply everything through by the square root of 2. Multiply 10 by the square root of 2 is just 10 times the square root of 2. Multiplying AC square root of 2 by the square root of 2, well, the square root of 2 times the square root of 2 is 2. Multiplying BC times the square root of 2 by the square root of 2 gives me 2 BC. And then remember, we're trying to isolate one of these leg lengths. And so I could divide now everything through by 2. Okay, 10 divided by 2 is 5, so 5 times the square root of 2. 2 divided by 2 is 1, so just AC. 2 divided by 2 is just BC. BC's left. And so AC equals BC, we knew that, which is also equal to 5 times the square root of 2. So we found the unknown side lengths. Both AC and BC are 5 times the square root of 2. Okay, So we're going to do one of these together. Another thing I did to kind of change the way our pear decks look, I'm going to try to stick with this kind of a format, is I've always had it like labeled vocabulary. I'm trying to label the examples. There's more than one, and then there's a practice on your own part. Okay, so we're now on slide 5, which is the last slide we're going to do together today. And then you're going to do slide 6, and then you're going to stop. And then we'll come back and work on this some more tomorrow. So for this example, it says find the unknown side lengths in each triangle. Well, there's only one triangle right here because I clipped this out of something else, so there's more problems. But we're just looking at this problem right here, which is from 13.3. You would find this problem. It's number 6 in there. You could find it. But we're going to do this one together. And so if we just look at the triangle we have, we're going to recognize that we have this 90-degree angle here. We have a 45-degree angle here and a 45-degree angle here. So this is, in fact, an isosceles right triangle. Okay, it's where the two leg lengths are equal, right? And then that would then imply that the two angles that are acute are also equal. So if you ever have a 90, 45, 45 triangle, it is in fact an isosceles right triangle. I spelled that right. Isosceles right triangle. I'm going to check. I don't always trust my own writing skills. Okay, so we do have an isosceles right triangle. Because it is a (45, 45, 90) triangle. And that's just referring to the degrees, okay? And I can even put like the little degree marks there. Okay, so 45, 45, and 90. That's an isosceles right triangle. And so when that happens, there's a relationship. We have a relationship between the leg lengths and the hypotenuse length. Okay, basically what we know is that the length of the hypotenuse right here and our two leg lengths, well, this is 2 times the square root of 6, so this is also 2 times the square root of 6. The relationship here is that if I multiply one of the leg lengths by the square root of 2, then I will get the hypotenuse. Okay, so our hypotenuse is this PQ segment. So PQ, and that's the only one we have left to find, right? Because we're trying to find the unknown side lengths. If I'm given one leg, I know the other leg is the same. And then also I can figure out the hypotenuse with just a simple equation. So we're going to say PQ is equal to, and the way they showed in the last example, they had, you know, PR is equal to, and then like QR, so they have like 3 pieces. I'm not going to do all 3 pieces. I'm just going to pick one of the leg lengths, okay? So I'm going to say PR, but then it's not just PR, it's PR times the square root of 2. So that is the special relationship. If you take a leg and multiply it by the square root of 2, that will give you the hypotenuse. If you're given the hypotenuse and you want the leg, you have to basically divide by the square root of 2. One way of thinking of it. And so we're going to substitute in what we know, which is PR. PR is 2 times the square root of 6. And so PQ is equal to 2 times the square root of 6 times the square root of 2. And now we just need to work with our 2 square roots and simplify it. So in the chat says 2 angles are equal. That means the triangle is isosceles. For an isosceles right triangle, if you have a right angle and then these are both 45, as an isosceles right triangle. They can only both be 45 here because remember they have to add up to 180. So 45 plus 45 plus 90. These 2 angles are the same because these legs are the same. That's the definition of isosceles. There's the 2 sides of your triangle. At least 2 sides are the same. They're congruent in their measure. Good question. Okay, so I'm just going to rewrite this now. I have 2. And then I'm going to take the square root of 6 and square root of 2 and put them together in the same square root symbol. And so I'm going to rewrite 6 as its prime factorization. 6 is the same as just 2 times 3, right? And 2 is a prime number and 3 is a prime number. So I'm going to rewrite 6 as 2 times 3. And then I'm going to put this times 2 here. Okay, and then when I'm trying to simplify a square root, there's an invisible index of 2 because I need 2 copies of any factor to pull it out of the square root. Well, I have 1 2 here and another 2 here. So since I have 2 factors of 2, I could pull a 2 out. So we have that same purple 2. And then I'm pulling out a factor of 2. And then I have left in the square root symbol just this 3. Okay, and there's one more thing you could do to clean it up, which is just multiply the 2 times 2 together. So this is actually going to be equal to 4 times the square root of 3, which is what I was looking for. This is the hypotenuse length. So this is 4 times the square root of 3. Okay, and now I've done what it's asked me to do, which is to find the unknown side lengths. Okay, I found all of them. They gave me 1, but from that I was able to figure out the other 2. You guys have questions on this example? Because you are going to now do a problem that's very similar. And you can use my work here to kind of help you figure out what to do. So what I'm going to do here is just go ahead and push you forward to the one you need to work on. I'm going to put you into student pace mode.